How'd you do on example 3? Okay, the main steps were find where it crosses the x-axis, and then distance in 1 or 2 dimensions is the integral speed, and in 2 dimensions speed is more like a Pythagorean theorem calculation of the horizontal and vertical velocity components, right? All right, B, or the next one, whatever you want to call it. How are we doing on the next one? Did you get x is 5 halves? Yes? Okay. And y then, how do you find y at 1? It's natural log of whatever x is, right? So it's natural log of 5 halves. So our final answer then is x of 1 is 5 halves, y of 1 is log of 5 halves. That's the position at time 1. Cool? Cool. Okay. Done with the last one or another minute? Another minute. Make sure you answer your answer, because everything's in vector notation. They say the position at time 2. I'm not sure if they want the position or the position vector. I guess they just say the position. I'm not sure whether they want a point or a position vector. It should be vector because everything else is vector. What'd you get for x at 2? Anybody? 0? 9? Nobody? No help whatsoever. 9? Okay, 9. We're clear. And y then? Yes?
Why do you have to assume that x is 5? Isn't that supposed to accurate?
Oh. Well, that's a good question. Am I overlooking something then? How do we know the position? So maybe they did mean to say position vector then.
You're not given, initial position or
Right.
anything.
So it should be the position vector we're finding, not the position itself, because we can't really know where the starting point of the vector was. Remember, vectors just give directions, not necessarily where they are. So, good point. Thank you. I didn't even think about that. What'd you get for y at 2 anyway? 4? Okay, cool. All right. If you could do that, then you could do most free responses on this, and they're pretty common. I got to say, they're usually one of the 3 free response BC questions is a motion problem, and that should be a nineable kind of problem. Would you then consider your notes here? This actually will take 2 days. First, if you didn't get 90 or 143 yesterday, I had 143 out yesterday, but if you need it, should I continue it? You got it. How about you people? Who has this? Okay. I think I actually have a lot of homework. You might tell them that. All right. Ouch for them. Okay. So here we go. This is the deal. This actually has two components to it. One has a kind of a you need a lot of pre-calculus precursor to get into it, and then there's a calculus-ish side. I think I'm going to do the pre-calc side tomorrow, but just to see how much time I need to budget here. Does the word combinatorics mean anything to you? Okay, combinatorics. You actually know some combinatorics, maybe you just don't know that. Okay, like the fundamental counting principle. Does that mean anything to you? That's not. Okay, so let me go here. I'll boil it down to a problem in your record. So if I had 3 people and I wanted to sit them in a row in 3 seats, could you do that? How many choices do I have for the first? 3. For the second seat? 2. For the third? 1. Do I add those or multiply? Multiply, because there's this, this web effect or this branching effect, right? That's the fundamental counting principle. Now, if I said, hey, I have 7 people to choose from, and I want to arrange them in these 3 seats, how many seating arrangements? What would that be? 7 times 6 times 5, all right? Now, what do you call that when you say how many ways to arrange somebody in an order? That's a permutation. Okay, now if I said I have 7 people over here, and how many groups of 3 can I make? Would that be more or less than the arrangements? More. Less. Okay, because permutations would consider Emma, Sam, Yulia different than Sam, Yulia, Emma. They would be counted differently. But I think you'd agree that would not be a different group, so we would lessen that organization number or structure number. And a group then is less than a permutation. And what do you call a grouping? Combination. Now, combinations are super useful in real life. Did you guys do binomial distributions and stuff? Yes. Did you do binomial probability distributions? Okay, it's great stuff. Okay, so we'll talk about this a little more tomorrow. But today, it sounds like it's all coming back to you, so maybe I don't have to do as much notes. All right, so today we're just going to do the front side of this, and here we go. Now, say theoretically that you're at the dinner table, and your mom says, so what is a Maclaurin series? or what is a Taylor series? Okay, and how would you answer that? I don't know. Okay, well then you have company, okay, because at my dinner table, theoretically speaking, maybe my theoretical wife asked my theoretical daughter, hey, what is this Taylor series? And he said, I don't know, it's all derivatives, stuff. And I don't know. It was incoherent babbleness, okay? That's it. She eventually worked it out. But that said, let me go back back and step back to make sure you understand. When you do a Taylor series or a Maclaurin series, your goal is to try and mimic some crazy function like sine or cosine or e with a polynomial function, which are generally happier and easier to work with, right? It's easier to plug 2 in to 1 plus x squared than it is to plug it into sine. You know what I mean?
Yes.
All right, now that's why you do Taylor's, just because polynomials can be made to behave like, they're called transcendental functions, by the way, not weird functions or achy functions, but that's why you do it. Now, today, we're going to try and mimic the behavior of a function like 1 plus x to some power. Now, you might be thinking, so you mean like f of x equals 1 plus x cubed, maybe, for example. Now, tell me why it would be a colossal waste of time to try and make a Maclaurin series for 1 plus x to the third. It's already a polynomial. Now, that said, you could take derivatives and all that stuff. And once you did your Maclaurin, what would it look like? It would be that, expanded. It would be 1 plus 3x squared. Now, the point then I'm trying to make is you wouldn't use a Maclaurin to model this kind of binomial because it's already a polynomial. We're going to use a Maclaurin on this for cases where this is something more like that. Now, what would that mean? We're using it to estimate square roots. Okay, that's beautiful. So really think of this, when I'm doing Maclaurin and binomial series, think it's a way to do not just a tangent line for a square root, but more like a tangent polynomial. I'm trying to match a square root function at lots of points, not just close to a point of tangency, but lots of points. You with me? All right, now let's just, rather than do concretely from the 1/2, let's just do this generically so we don't have to do each one differently. We're going to make a general, what do you do when you have 1 plus x, a binomial, 2 terms, 2 power? You standing for power. You with me? All right then. Now if it's Maclaurin, then my goal is to get f at 0 plus f prime at 0 x minus c, which in this case x minus c is x minus 0, or just x. So f prime at 0, x to the first over 1 factorial, plus f double at 0, x squared over 2 factorial. And so that is the Taylor series idea. But when it's around 0, it's all called point. You with me? Now, the more complicated the function is and the derivatives are, the more you should keep it organized. This has very complicated derivatives. So this is what I'd like you to do. Go off to the side and say f at 0. We're going to chart what we're doing. We're going to show the derivative, and then we're going to evaluate. So, for example, when I say f at 0, that's 1 plus x at 0, which is, 1 plus x to the p, 1 plus x to the p, evaluated at x of 0 is 1 to the p, or 1. Okay? F prime at 0 is p, 1 plus x to the p minus 1, evaluated at 0. Evaluated at 0, that is p times 1. Oranges. F double at 0 is p times p minus 1, if you're not distributing, times 1 plus x to the p minus 2. Evaluated at 0 is p times p minus 1. Do you hear where I'm coming from? F triple should be enough before we go back to right. F triple would be p times p minus 1 times the next power come down, which is p minus 2, 1 plus x to the p minus 3, evaluated at 0, which is p times p minus 1 times p minus 2. All right. Now let's go write our Maclaurin. Excuse me. So f at 0 is 1. Okay? That is to say, at x equals 0, they should have the same point, and I think you'll agree that our y-intercept needs to be 1. All right, so cool. Then the next is f prime, which is p, x to the first over 1 factorial, plus p times p minus 1, x squared over 2 factorial. Let's do one more, p times p minus 1 times p minus 2, x cubed over 3 factorial. You tracking?
Yes.
All right. Give yourself a plus and a dot, dot, dot. And let's go to a general term, which is a wee bit ugly. Let's do the easy part, the denominator. If I looked at the nth term, then the denominator is n factorial. And we're starting at 0, sure. Okay? The x to the n is also going to be there. I didn't give myself enough room for dot, 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 but it does continue after the nth term. It's infinite, right? Now let's get into the coefficient or the derivative part. After, let's say for p greater than, actually for n, not p, sorry, for terms after this, after where I stop, so for n's greater than, what, 3? Okay. In other words, I'm saying a general term for everything after these original. You follow? What would everyone be? How would everyone start? P, and then they would be followed by p minus 1, and then p minus 2, and you keep getting new factors. How many? Well, that kind of depends on how many derivatives you've taken, right? But they all have an ending point. So we're going to jump to what the ending factor would have to be. Now, to get this, look here. Here, the last factor was p minus 2 when it was x cubed. Here, it was p minus 1 when it was x squared. So generally speaking, that last factor is p minus, depending on how you, yeah, p minus n minus 1. Now, does that n minus 1 need to be in parentheses? Yeah, it does. P minus n minus 1. And if I check that, I feel like that works when n is 3. P minus 3 minus 1 is p minus 2. That's working. That works there too. You see? Yeah. Okay. Now, tomorrow we'll talk about what the heck that is. We're not going to go to summation notation there because the summation notation is a little less than obvious, but just taking a peek at it, what do you, I mean, this top, what does it kind of feel like? P times stuff below it. Kind of factorial, but not all the way down, right? And when it doesn't go all the way down, it must have canceled with something below it, yeah? And so that's actually where permutations and combinations come in tomorrow. Not permutations, actually. But we'll talk about that part tomorrow. Let's go to what a problem will look like, all right? Keep that in front of you. I'm going to actually copy and paste that to my next slide. And let's go to using this bad boy to estimate. All right? Now, say you wanted to use a binomial series to estimate 1.25 square rooted, accurate to 3 decimal places. Now, I think yours does not say accurate to 3 decimal places. Is that correct? Yours says error less than 1,000?
Yes.
I need this, the Saxon book especially does problems like this. So let me talk about that real quick. I think I've talked about this with a few people here and there in several periods. But accurate to 3 decimal places means when you look at their readouts are the same through the 3rd decimal place. So say 2 numbers had these numbers, but actually I'm going to go call that 4. Okay. But then after that they were as different as possible. So I'll say this one is just 9s forever, which is as different as possible from 0s forever. You with me? Now, in terms of translating this, if these are accurate to 3 decimal places, then the difference or the error between them would be something like 0.0's the difference is 0.0009s forever. You with me?
Yes.
Now that would mean that the difference is less than, what is this, if I were to clean this up, wouldn't you say that this is just barely less than 0.001?
But I thought that like
Yeah.
the end sign is actually one.
I'm worried
like
you're gonna
with,
say that. So let's say it's not an ampersand. So accurate to 3 decimal places is the same as error less than 3 decimal places or error less than 1,000. So if it says accurate to 6 decimal places, then that would be error less than 1,000,000. All right, you with me? All right then. Now this is really a problem of organization. You can get the answer, but boy, you can definitely lose the person reading it along the way if you don't communicate your thinking clearly, all right? So I'm going to walk you through exactly the work I would like you to show and in the order in which I would like you to show it. So let's first get clear what you're estimating. All right, the square root of 1.25 is like, actually, and I should say, how does it fit with the binomial? That binomial. All right, so maybe I should have, before I said square root of 125, what's the function? As a binomial, the function is 1 plus x to the half. And the 0.25 is what I'm going to deal with later in my estimate. But the baseline function is 1 plus whatever change from 1 to the half. You with me? All right. And I'm trying to, when I go to estimate the square root of 1.25, that would mean f at 0.25. You follow? Because that would be 1 plus 0.25 to the half, and that's 1. All right, now, I have clear what I want to estimate. I say the function is 1 plus x to the half, and I'm trying to estimate f at 0.25. Now you make your Maclaurin for this function, and that's at any x. Again, we're not worried about the 0.25 till way down the road, right? So when I go to make my Maclaurin here, using a p of, what's the power here? 1/2. Okay, remember this is to fit 1 plus x to any power. That which we just did is 1 plus x to a power. In this case, I want 1 plus x to a specific power, a power of 1/2. So, I'm trying to do this problem for a power of 1/2. Now, surely, if you don't want to use this blueprint or formula per se for the binomial theorem, could you go off to the side and just do the derivatives from scratch and front work it out? Sure, you could. But let's save ourselves some time here. 1 plus this first term, p is 1/2 x to the first over 1 factorial. The next is p times p minus 1, which is 1/2 times negative 1/2. X squared over 2 factorial. The next term is 1/2 times negative 1/2 times negative 3/2 x cubed over 3 factorial. And I could write a general term if they ask me to. And it is something like, it's always going to be 1/2 times negative 1/2 times negative 3/2. And I'm going to keep multiplying by junk until my last factor, which is 1/2 minus n minus 1, x to the n over n factorial. Hey! All right, so there's my Maclaurin. Now, I plug in what I'm trying to estimate, which is to say plug in an x of 0.25 or 1/4. go with all fractions. You follow me? Right. M at a fourth is 1 plus a half times a fourth over 1 factorial plus a half times negative 1/2 times a fourth squared over 2 factorial plus a half times negative 1/2 times negative 3/2, 1/4 cubed over 3 factorial. And we can keep going. You can write the general term, but it's not crucial that you have that right now. All right? You with me? All right. Now let's talk communication of your estimate and why the number of the n you used. This is where I want it clear, so I don't have to grade a bunch of all over the places. All right. If it says accurate to 3 decimal places, what does that mean? Error bound. They want me to establish, make sure that the error is less than some mark. So that means they want to talk error bound. They don't want me to say, hey, I feel like doing 3 terms, I'm going to go for it. They want you to decide how many terms exactly will you need, or minimum at least, will you need to get the error below that standard. All right? Now, the only way that's going to happen is if this series is alternating. Is it alternating? Now, surely that's not alternating. But after that, and forevermore after, does it start to alternate? Yeah, that's negative. This is positive. That's negative. So after n equal, after, I'm going to say, I'm not sure if n means the term number of, so I'm just going to say after the second term, they do alternate. Okay, how's that sound? And do the terms decrease? Is each term less than the one before?
Yes.
Yes, for sure. And do the terms go to 0? Yes, they do. And so it satisfies conditions of error bound. So if I wanted an answer or an estimate that was less than 1,000th off, then I really need to find the first term that is 1,000th or less, right? Or less than 1,000, yeah? And then once I have identified this term is less than 1,000, that's the error bound. And so do I add through that term or all the ones before that term? Before, okay? So that's what I'm going to do, and then I'm going to write up my analysis. But I need to find the first term that's less than 1,000 so I know how many terms to add for my estimate. Are you with me on that?
Yes.
Okay. Now, here I go. I can save you some time there, because these can be major time eaters if you're not efficient with your time. After we look at the first term, obviously that's not less than 1,000. That's an 8. That's not less than 1,000. Here, I don't know, but I'm starting to get into I don't know kind of territory, right? Now, say that wasn't it, and then I found that when plugging this one in, this one was less than 1,000. That would tell me, okay, I would need to now add how many terms? The first 3. Then, when I go to add them then, won't I need that anyway? So my point in terms of efficiency is this. This one I don't really need to calculate, but do calculate that and store it because you're going to need it later. We're not going to just see if it's less than 1,000. We're also going to be using it in our sum later. So would you get out your calculator and put that third term in? The first 2 are trivial and fairly straightforward, so I don't feel like I need to put those into my calculator. But the third one I do. So goodness. Oh, goodness. There you go. Okay, so 5, negative 0.5. The ones with the square, is that what I said to go through? Okay. 0.25 squared over divided by 2. Okay. Next. Because you get negative 0.007. Negative 1?
Or negative 1/1
Is that what you did? Oh, you use fractions.
Yeah.
Okay, cool. It's fine. Either way, it's fine. All right. Now then, is that less than 1,000?
No.
Yeah, I mean, don't worry about the sign, okay? Is 7 thousandths less than 1,000? It's not a trick question. 7 is not less than 1. You agree? Okay. So it is not going to serve as an error bound, which means we need to look at the next term, right? All right. Now, in terms of, again, expedience, rather than start, again, retyping everything, I think it's easiest, I find it's quickest to just recall the next term, or recall the previous term, and then just change it a little. From here, don't we now need to also multiply in, we need to multiply in by some more things. What else are we going to need when we go to the next term? Negative 3 halves. So we're going to bring in negative 1.5. What other kind of change are we going to need to do? Change the exponent to 3 and change the denominator to 3 factorial or 6. If you wanted to go factorial, that's fine. But that gives you negative 9.765. Oh, you know what I just didn't do? I didn't just follow my own instructions. I said you wanted to store this. Doggone it. Store that. Even though that wasn't the one. Doggone it, I'm so stupid. What the heck is that none thing? Even though that wasn't the one, I'm going to need it later, so I should have stored that to A before I should and went changing. All right, so at any rate, wouldn't you agree that QE kind of term is less than 1,000? All right, that means then that could be my error or the first omitted term, and I want to add all the terms below it for my estimate. And so now let's do that. Would you add the first 3 terms? 1 plus, what's the next term? 1/8? 1/8 plus A. I get an estimate of 1.1171. Do you all agree? Okay. Now let's talk about writing it up and with good justification about what I did. Come on, baby, move. Oh, sorry. How do I move this? All right, sorry. All right, so what my estimate is and why. So first of all, I would say something like this. Because, it's probably bad grammar to start with because, but you get the idea. Because this series is alternating, the terms go to 0 and decrease. And again, you could write that in more like plain old English, which is to say because this is an alternating series whose terms decrease in absolute value to 0. The error in S3, we said we're going to use 3 terms, right? So here, S3, S minus S3 is less than or equal to A4, which is 0.00097 or something like that. Is that right? Yeah. Which is less than 1,000. Maybe I should have given my estimate first, huh? Am I putting the cart before the horse here? Because the series is alternating, the terms go to 0. The error in S3 will be less than 1,000. S3 is 1.1171. How do you think it would read? Would it read better if you gave the estimate first and then you say, yeah, I should have done that first, huh? Sorry. I'm just gonna do that. I wish you could do that, but, the I guess that the best case would have been the square root of 1.25 is approximately S3 of 1.1171, and then why I've used S3 is the following. With me? Now, if you were to throw that in your calculator, what is the square root of 1.25? Okay, now that feels like not accurate to 3. And that's why I changed it. I think that's why I didn't like this wording. This actually is accurate to answer your question. It's accurate to less than 1,000th, because if you take that minus our answer of that guy, it is 8.4648, which is to say less than 1,000. I think I just explained accurate to 3 decimal places incorrectly. If I'm not mistaken, I just showed that it is not the same to 3 decimal places, but it is error less than 1,000. Yeah? And that's because of the rounding issue. That's what I forgot to put in. Forget that 3 decimal places now. At least I remember why I changed it to 1,000. I didn't even want to get into this. This lesson's hard enough. So ignore this over here, but your notes are fine because I changed it to 1,000. All right. Are you tracking there? This can be pretty stinking difficult, but with practice, it'll go great. We have 1 minute for questions on 142. None? Okay. Turn in 142. All right. We'll try and get caught up with questions. So you have 142 and 143 is tonight.
43 is
Tonight. 143 extra practices tomorrow. Do you think you
They
could
used
get
my
this?
yesterday too, and he said the same exact thing.
but I have a horrible memory.
Oh, we'll have to be in
They
for
said
that.
it just runs mine.
Miles just hit you up. So, 142, we'll go over tomorrow, hopefully 143 also. And I'll take the back of the notes. And you'll have time to work on the extra practice. Have a good day.
Oh my God. Ian, look at that. Look at that. Oh, yes. Thank you.
You're welcome. Have a good day.
It's been a long day. It's been a long week.
Oh, no.
Ooh.